So the agenda for this CES will be top-down design and specifically using wavelengths to accomplish that. So the agenda looks like this. We'll first go cover an overview of the top-down design approach, what a top-down product structure looks like. We'll cover wavelength features and some of the descriptions for those features. Then we'll go ahead and run through a demonstration, actually going through the motions, the clicks, and lastly, we'll close with some tips and recommendations for using wavelengths. All right, so first thing to cover here is two different design theories that we have, a bottom-up theory versus a top-down. So bottom-up really focuses on creating the subcomponents first and assembling and pretty much putting together that high-level design towards the end. So it's a microscopic data approach rather than top-down is macroscopic or driven by requirements by a systems engineer that flows down those features, datums, coordinate systems, critical dimensions down to the subcomponent level. So this is an example of the methodology of the top-down design for an engine block here. So you can see starting at the top left of this matrix, we have an envelope that contains the size of the cylinders, where the pivot shaft's going to go. So all that is going to now get driven down into envelopes for your subcomponents. And if we move down this block here, we can see the detail design being driven by those requirements, right? So at any point, the volume changes at the skeleton or at the top level, your detail parts should be updated and that should be reflected, okay? So this is very critical. This methodology is critical for large assemblies and we're working with multiple subsystems, critical interfaces to communicate those across those subsystems. So this is a very useful methodology here. Okay, now let's talk product structure. So the objective of the top-down product structure is to communicate and control key design requirements. So those should be flowed and controlled from the top level down to the sub-assemblies, components, and you build out your detailed parts. So for a design like an aircraft here, we have multiple subsystems. We have the fuselage, the wings, the rudder, the stabilizer, the engines, right? So we want to make sure that we have a methodology to communicate not only interfaces, but those top level design requirements. So for this session, we'll take a look at the stabilizer and have that pulled from the rest of the subsystem with the rest of the aircraft, and then we'll grab that and we'll extrapolate down into one detailed part. So you'll get to see the product structure, an example of that. Okay. So there's a lot of different methodologies and across different companies. Larger companies may have something different than a smaller company, depending on the size of the product itself or all the different subsystems. So here's just an example of what a top-down product structure could look like. At the very top level, we have what we'll call the layout level, and this will communicate requirement. The main intention for this is to collect and communicate requirements. So here we'll have interface requirements and the skeleton or the datums that will be pushed down to the lower levels. So depending on your use case, you may have something called an interface control document, and that can be driven by a PDF document, a drawing with key dimensions, key tolerances, datums, and you can also have a model as well. So this can be the envelope model that's driven by your aero team or surfaces team. You can have that in this layout level. So ICD in this case will contain all physical interfaces needed to design and build a system. So this is your bolt patterns, your envelope, your datums, things like that. Then what we'll have just in that same layout node is the MDF or the skeleton model. So MDF stands for model datum features, or commonly known as a skeleton. So these contain your critical datum features necessary to build and design the system, as well as control critical dimensions, sketches, features, things like that. So in the previous slide, we saw the ICD captured subsystem coordinate system. It captured the envelope, and it captured a datum point. Now at this level here, we grab that and we start building out our sketch, our skeleton here that will define the datums, where these ribs will be located, where that spar will be located, the closeout rib, and pretty much build the infrastructure at this level here, at the skeleton. Now, still within that layout node, now we'll have a collector, also known as a end item collector or assembly collector. This is your deliverable. This is the product. This is what captures your structure, your electrical components, avionics, your wire harness installation. So this is, like I said, the product here. So now at that next level there, we have the subassemblies, the detail parts, the hardware. This is where you'll have those drawings created at the detailed part level. And pretty much this is what the structure looks like when you're trying to manage and communicate top level requirements. So these requirements are flown down to the component level from the ICD, and the system features and datums are flowed down to the component level from the MDF or the skeleton. So in this case here, we saw the ICD contain the envelope, critical mounting points, and the coordinate system. That is then communicated to a skeleton that we build at the top level. Then from there, we push those datums, we push those sketches, those points to the component levels. Those are all handled or all using the wavelength feature in X. We'll take a look at how that's handled, how that's managed and created. Okay, so now let's talk about different wavelength types that we have in NX. So first thing is we have a position dependent type. And the feature for this is the wave geometry linker. This is used in layout files from reference geometry and to the skeleton file. So really, this is within the context of the assembly that you're creating this versus something that is position independent. This, you'll have the wave mode feature, which will push geometry outside of the context of the assembly. So if you're working with a different subsystem or a different structure, product structure, pushing out just the geometry itself will be managed using the wave mode. So there's a way to push geometry, pull geometry from that versus the wave geometry linker. You'll see that it's position dependent. So you have to be in the context of the assembly, and you have to have that product structure that we saw earlier. Then we have interpart expressions. So these are your formulas, your expressions handled in your part level that gets pushed down to your different components. So we'll see an example of that being used where the thickness of a part is captured in an expression and then pulled in a different part. So that relationship is kept. You're not pulling bodies, you're not pulling surfaces. Instead, you're pulling an expression that can be managed at a higher level. Okay. So the first and the third, those are part of the demonstration that we'll go over. So we'll take a look at those two features. And the demonstration here, the objective is to create a detailed part, or in this case, a rib, using wavelengths and a top-down design approach. So again, we'll start off at the layout level, take a look at the skeleton model, then from there, start building our rib from those datum features. Right. Let me go ahead and jump to NX. Okay, so here I have my layout assembly. This is for the stabilizer. And in this node, I have the ICD, the MDF, and the end item collector here. So first, let's take a look at the ICD. This here has the aircraft coordinate system. It has the stabilizer envelope that our aero team gave us, and then it has a mounting point. So of course, for something in production, you'll have a lot more data in here, a lot more, I guess, requirements. You may have an OML, IML, bolt patterns for the closeout rib, things like that. So this is just an example of what that would look like here. And then from here, we have the MDF, which is built from that ICD. So if we take a look at this MDF1 here, we have our aircraft coordinate system. We have our linked body, which is that stabilizer envelope. From there, we created a stabilizer coordinate system. So this is our subsystem coordinate system that we can build the rest of the subcomponents from. We can use it for positioning. We can use it for reference. So we have that on here. And then we have a sketch that will define the placement of the ribs. So these are our datum planes driven by the sketch that is driven by the envelope. So if at any point here, we need to change, we need to add a rib, remove a rib, change the position, we control that from this skeleton here, this sketch at the MDF level, right? So if I need to go ahead and update this to 50, I can do that, hit finish, and that will move my datum rib 1 here. Okay, so that's the MDF here. Now we have the end item collector. This is the collector for your structural components, your electrical components, have them, things like that. You can go ahead and add more depending on what your product or deliverable will be. You may have some more assemblies down here. So we'll first take a look at the structural assembly here, and the goal is to create this rib here. So this component, right? So we'll first start off with creating a new part, bringing this in, and then using wavelengths to start building out or pulling those requirements. Okay. So we can go ahead and first go and create our part. So here, we'll just call this ST00 rib 2. Save this. Let's add this to our assembly. And here we'll just add this to the world coordinate system. So basically, we're saying that the world coordinate system of the rib 2 will be the same as the world coordinate system of the structural assembly. Go ahead and bring this in. Now, this will be linked to my world coordinate system, so I can go ahead and click OK, and then I can fix this in place now. Okay. All right, so now this is fixed in place. I can go ahead and make this the working part now. And what I want to do at this point is start grabbing the the envelope, the datum planes, things like that, so I can build out this rib. And so I'll go into my assemblies tab, click on wave geometry linker. I'll start off with the envelope here. So this will be your body. This can be sheet body or solid body, and we'll grab the sheet body in MDF1. Okay. Here, this associative setting will determine whether it's a live link or a broken link. So here we'll have this checked on for now. We'll click OK. Then let's go back and grab the datums. So I'm working with this here. So rib 2 will be positioned here and relative to that spar. So I'll grab both of those. Okay. So now I can go ahead and I think I also need the coordinate system. Yes, so I'll grab the coordinate system and then I'll open this in a separate part here. Data. Okay, now let's go ahead and open that. Let's see. There you go. Okay, so now we go into our part navigator. We can see our links. Our links are currently intact. They're up to date. You can go ahead and check that column here. If they're broken, you'll see this gets updated. If at any point the planes or the envelope changes, you'll see an out-of-date notification there. Okay, so now I can go ahead and start creating my sketch. So I know my rib is going to be here. I can basically build out those my feature there. So I'll start off by creating a sketch on this plane, then make this the horizontal feature. And I can start including these datums. So I'll click include. I'll include this. I'll include this datum here and this datum here. Okay. So now I can start building my profile. So I can build my profile from here. I want this to end where the thickness of that rib ends. So I'll just position this somewhere here for now and close this out for now. Okay, so I want the thickness of this to be 12 millimeters. Grab these two. Make that collinear. And so now I just have to meet up to where that offset. So what I'll do is I'll create an offset feature relative to that. And I know it's 15 here, but instead of manually controlling my dimension, and instead of adding another linked feature or a linked face, what I can do is go ahead and go to my expressions, and I can bring in an interpart expression. And so now when I look for my let's see, what part is it? 5384. When I search for the part that's of that leading edge closeout rib there, I can go ahead and click on that part, look for the expression I want, and here it's controlled now at this part level. So the thickness of the leading edge rib is 15 millimeters. So now that's brought in. And now that's controlled in this offset curve. I can go ahead and click OK here. I'll make this a reference curve. And what I can do is have this be collinear to that there. Make this collinear, and let's make that collinear or coincident. All right, so now I have my sketch, and I just need to constrain this here. Okay, so now I have that profile created. I can go ahead and extrude this out and use the trim function to trim based on that envelope. So I can go ahead and do that. Here, we'll say this is a symmetric value. We can also do until next, but I find going over and using the trim function a little bit more stable or robust than using the until next feature. So I'll go ahead and use this for now, and I can use that trim body. So select my extrude, select the envelope as my tool. I can go ahead and click OK. Let's hide these. And now I can go ahead and finish this off with a shell feature. We'll say that is 1 millimeter thick, and we can apply some fillets in here. I guess just to finish this off, I'll just add those two. Use the select predict options feature to grab that edge there. And let's just make this something like that. Okay. All right, and of course we can go ahead and add some more details, right? Our lightning holes, our where our rivets will go. But for the sake of time, this pretty much covers the the process, right? We have our links, our envelopes, our ribs. Those are position dependent. That's why we use that wave geometry linker. And now we can take a look at our rib here in this layout structure. Let's hide the MDF. And we can go ahead, just to clean this up a bit further, we want to make sure our reference set to model, and we're not seeing those links, those datums. We're just seeing that rib there. Well, that concludes the demonstration, going from the layout, the ICD, the MDF, creating the sketch, using those to define the datums, the positions of the ribs, using interpart expressions to pull that thickness, that position of that top of that rib there, and build out our extrude using the trim function, trimming around the envelope. All right, let me go back to the presentation now. Okay, now some quick tips for using wavelengths. So wavelengths, if you don't have a plan at the start, it can be very detrimental down the line when you have to manage a lot of different links, broken links, updates, and especially if you're in an uncontrolled environment and don't have Teamcenter or a PLM system to handle this, this can be a nightmare when you're releasing components. So you want to keep that in mind. Wavelengths should be used in a controlled environment. So let's go over some tips here. You always want to link the bare minimum needed to accomplish the task. So points, datums, curves, etc. You want to avoid linking solid bodies. Those can bottle up your the load times and the file sizes of your components. Use the link geometry for reference only, not to directly model your part. So if you're linking a curve, don't use that curve to extrude your part, right? Use that curve as a reference I used the datums as references. The interpart expression, that offset, I use that as a reference. So you're not directly extruding from a linked component. Use layouts, skeletons, master files to prevent circular references. It can start looking like a spider web. It'd be difficult to track if you don't have a methodology, a product structure in place from the get-go at the beginning for your team to grab those requirements. Worst case scenario is you're working with outdated interfaces, circular references, and then you have a bunch of warnings or error messages in your model tree. Utilize the delay link update feature to avoid links updating sporadically. So again, you want it to be controlled. So go ahead and toggle on that delay link update. When there's an update that does occur, you can catch that and not, catch that right when it happens rather than it happening while you're making edits. Ensure the parent component is controlled. So this can be released, frozen. You want to make sure that if you're linking to an interface, for example, or bolt pattern, and you release that bolt pattern should not change, right? That should be released, that should be frozen. You shouldn't be releasing something where the dependency of that is still being worked. So again, this is where team center is critical, and having a controlled environment is critical. Use the interpart link browser to evaluate these references and your parent-child relationships. So as you're creating wavelinks, you want to be able to track those, what's being referenced, what's outdated, things like that. So using the interpart link browser enables you to evaluate those. Break links or use the wave freeze before releasing a part. So again, if you're releasing a part, you want to make sure you're breaking all those so you have something frozen, something static, rather than something that can be changed after release. So that can cause some issues. So best practice is to freeze or break those links. And then lastly, delete any unnecessary links before releasing the part. Right? If you can avoid it, avoid it. You only use wavelinks when you're communicating critical features, requirements. Besides that, you're pretty much boggling your system. So if you can avoid it, and just have it controlled at the top level. And then just lastly here, the interpart link browser and the wave freeze features, those require a wave license, and the wave mode that enables you to be position independent also requires the wave license. So if you're interested in that, send us a message at info@saratech.com or here after this presentation. We can provide more information on the differences, the benefits of that wave license. And that's all I had. I will open it up to any questions that are out there.
We do have a few questions. The first question is, how do you break a link?
Yeah, that's a good question. So breaking a link, you can do that in the association feature. So for example, these are all links here. If I want to break this stabilizer envelope, what I can do is expand the settings down here, uncheck that, and this is letting me know that I'm breaking this link here. So if there's updates to the envelope, I will not, those won't flow down to this level here. So this is important when you're releasing. If there's something in work, then having that on may be beneficial.
Great. And then our last question, how do you evaluate existing links in an assembly?
Yeah, good question. So that one is managed through the interpart link browser. So for example, I've created some links in this layout assembly, right? So if we want to go ahead and do an audit of that, we would go to our sublease tab, go to more, and go to the interpart link browser. This here will give us a report of the parent and child relationship, the references, and what the link status is. So I just broke this stabilizer envelope. So this is telling me that my parent part is that ICD, that sheet body, the link is broken, and I can take a look at basically all the links at this level here. So if you're linking to an out-of-date, if you have an out-of-date link, if you have an active link, if your parent part is non-released and should be released, but this is the place where you'll do those audits, do that checking. Just keep in mind this requires the Wave license. So having this tool available could be beneficial, could be worth that license. So you're ensuring you're releasing to the appropriate parent components.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/